Now, in this video, let me give you a quick introduction about what is electrostatic potential difference. So, I will explain this with an analogy of gravitational potential difference. Now, what is gravitational potential difference? Let me give you an illustration. We have an object placed at a height of h above the surface of earth. Now, the moment you drop the object will come down to surface. Okay, initially the object is h above the surface of earth. Now it is 0 meter, 0 distance above the surface of earth. Now, how much work is done while coming down from a height of h? We will see. What is the equation for work done? Work done is equal to force into displacement. And what is the force while it comes down? The force is mg. Who provides the value on which object? Earth attracts the object downward in this direction. So the force has been exerted by Earth on this object in downward direction, mg. And with this force, what is the total displacement the object has made? That is h. So mgh. So mgh, this much joules of work is done. Now, who has provided? So we know that to do a work, we need energy. Now, who has provided energy for the object to do a work of mgh? The potential energy stored inside the object has given the energy for the same object to come down from a position of this till here. What is the potential energy? We know mgh. See, mgh is the potential energy. Using this potential energy, the object has came down from this position to this position. Now, we know that from this example, object from mass do travel from higher potential to lower potential. Clear? Similarly, in the case of electrostatic field, we have an electrostatic field in this way. I am keeping a charge here, Q. Now, this will be exerted by a force. If the value of, okay, I forgot to mention this. This electric field is uniform electric field. What do I mean by uniform electric field? The value of electric field at all this position is constant. It's the same value of electric field. Okay. Now, when a charge is being placed in an electric field of E, it is exerted by a force of Q into E. This we have already learned in chapter 1. So, QE is the force exerted on the object by the electric field. Now, this object will move from this position to this position along electric field, because we know the direction of force will be along electric field. Let me give you the equation. F is equal to Q into E. So, F is a vector. It has both magnitude and direction. Q is a scalar. So, what is the direction of force? That is simply the direction of electric field itself, because Q is a scalar and E is anyway a vector. Now, object will move from this position to this position. One thing is, from this analogy, one thing is very clear. This is at higher electrostatic potential as compared to this point. Now, let us prove it. So, I am keeping this equation, this process very simple, as we are going to do a work. Okay. Now, I am going to do a work from this position to this position. Let's say I am placing a charge of Q here, small q here at this position. Let's say this is position B and this is position A. Now, I am moving an object after applying a force on Q from B to A. This is not an object, this is a charge. Now, in this, why I have taken this example? Because in this case, I have to apply a force. Why? Because see, whenever a charge is placed in an electric field, this is very important. Whenever a charge is placed in an electric field of E, by the moment you place it, it is being experienced, the charge will experience a force of QE in this direction. So, it has a tendency to go in rightward direction. Now, for us to bring the object from B to A, we have to apply a force in this direction. Then only I can balance the force applied by electric field, which is in this direction. Now, I have to apply a force in this direction. okay, to balance this force, then only I can bring it from B to A. And what should be the value of the applied force with respect to me? That should be QE in this direction. So basically direction of E is in this way and my force should be in this way, opposite to the direction of electric field, the actual electric field. I am applying a force in this direction. Now while bringing the object from here till here, I have to do a work of W. So that is WAB. WAB means work done in bringing an object from B to A. Now electrostatic potential difference means, once again let me explain it to you. Potential difference or electrostatic potential difference between 2 points is nothing but work done in bringing unit positive charge from point B till point A. So in between A and B, the potential difference is nothing but work done in bringing a unit positive charge from B to A. So better what we will do, we will find the value of total work done in bringing Q charge, then divide, so value work done to bring Q charge from B to A, then we will divide it with Q. So it is equal to the value that we may find out for 1 coulomb. Okay, now what I am going to do, I am going to place Q charge. So I will find out the total value to do the work to bring it from B to A, and after that I will divide it with Q, so that I will get the value for 1 coulomb. I hope it is clear with you. For Q coulomb we will find the value, then divide it with Q, then we will get it for 1 coulomb. So for Q coulomb of charge to move it from here to here is nothing but, see, work done of WQ from B to A. So WAB means from B to A. So this will be the total work done to bring a charge of Q from B to A divided with Q. That will be the potential difference in between A and B, WAB. So WAB can be written as VA minus VB. So what is VAB? Potential difference in between A and B. That can be written as VA minus VB. And what is the value? Value is nothing but work done in bringing 1 coulomb from one position to another position. Here in this case from B to A. So instead of doing it for 1 coulomb, we are doing it for Q coulomb and going to divide the whole value with Q. Now how will we get the value of work done? If you know the force and displacement, that is F dot ds will be dot product of force and displacement will give you the value of work done. And what is the force here in this case? Q is the value of force, right? So force by which the electric field exert force, the value of force that the electric field exert on Q is nothing but QE, and QE is the force. So this is nothing but work done is equal to force dot displacement. So here in this case I am going to mark the displacement as dr, a small value dr. So F dot dr divided by Q. And what is the value of force that we have to apply? QE, right? And QE is in this direction. So basically we have to apply minus QE. QE is in this direction, minus QE is the value we have to apply. Okay, so minus QE into, I hope that concept is clear with you. QE is in this direction, but for us to keep the object, to move the object from B to A, we have to apply the value force in this direction. And as QE is in this direction, the value which we are applying is opposite to QE, that is QE in this way. So force is this one, and we are going to give a displacement in this direction. We are applying a force minus QE in this way, and displacement is this. So QE into dr divided by Q, and Q will cancel. What is the value? Minus E into dr is VA minus VB. So it's a change, right? I am going to make it as dV. dV is nothing but any potential difference in between any 2 points, not only A and B, any 2 points, dV is nothing but E into dr. So from this I can rewrite it as E is equal to minus dV by dr. So this is again a very important relation. What does this mean? See, when electric field is positive, okay, see, electric field is positive, this dV is negative, which means along electric field the potential decreases. When E is positive, dV is negative, which means along the direction of electric field, the potential decreases. So which means here this is the direction of electric field, this is at higher potential and this is at lower potential. Along the direction electric field decreases, opposite to E electric field increases. That's all.